Okay,
That's a transition.
let's begin.
But I also don't know if you the line on top.
So,
Show us.
just an FYI, I believe I was using this term, but these all mean the same thing. Different people call it different things. So the steady state matrix is the same as the stationary matrix, is the same as the stationary vector, the same as the steady state vector. It's all a species of eigenvector, so that's another thing that you might hear called. Your textbook probably uses this one, I believe. And this packet is actually from the online version of the textbook. So if you see this mentioned, they're talking about that. Just so you know. Yeah, final December 13th, this classroom, 9:30. It's an hour before usual class time. And test 2 is a week before that. Test 2 is Friday coming. And problems like these you'll need to know how to do. So I want to make sure you know how to do them, as well as how to actually write it down, so I know that you know what you're talking about when you write it down on a piece of paper. So let's start with problem 1. And this is just an excerpt from the rando. This is from the rando practice problems. So there are other 2 mock tests. Hopefully you've done that already. If not, definitely try to get it done by tomorrow. Problem 1. So we have a transition matrix. Solve the equation to find the stationary matrix. That's what it is. And the limiting matrix P. So remember how we find the stationary matrix? You don't know what it is, so you just call it XY. You're going to multiply by the P. But it is the guy that he transitions to himself. So you pretty much want to set up that matrix equation. S times P equals S, which is what it mentions here. I'm not going to tell you that, by the way. So this question actually told you how to do it. Solve for S and S times P equals S. I'm not going to tell you that. I'd probably just tell you solve for the stationary matrix. I'd expect you to know that that's how you do it. And so now you multiply this out. 0.5x plus 0.6y, 0.5x plus 0.4y equals xy. And so that would mean 0.5x plus 0.6y equals x, and 0.5x plus 0.4y equals y. I can bring x on one side over here. So this would be minus 0.5x plus 0.6y equals 0. And remember, the peculiarity of these problems is that if you do the second equation, you'll actually get a multiple of this equation, so you won't be able to actually solve it. So the trick is to actually note that because this is the state, these are all probability states of a certain situation, they must add up to 1. So that's always a second equation that you can use. Which is not going to be given to you, it's just by you knowing the nature of what S must be. It is the state, the probability of being in all possible states at the beginning. So it must add up to 1. So basically now, you think of this as the system of equations and you want to actually solve that. So I can multiply this by 10. And 1, 1, 1. I would take row 2, well 5 row 2, plus row 1. 5 times this plus that is 0. 5 times this plus that, 11. 5 times this plus that, 5. So you immediately get your y is 5 over 11, and your x, because that's to add up to 1, has to be 6 over 11. So that would mean your stationary matrix is 6 over 11, 5 over 11.
Do we have to use matrices on the test?
No. Not to do something like this. What would your P bar look like? We had a theorem about that. Yeah.
Is it just like S in both rows?
Yeah, it's like every row of the transition matrix is now populated by S. So it's 6 over 11, 5 over 11, 6 over 11, 5 over 11. So that's pretty much if you keep multiplying P by itself, P times P times P times P, and keep going, it'll eventually become that matrix, or it'll keep getting closer and closer to this matrix if it never actually gets there.
Jhevon,
Yes?
how did you get that negative 0.5x plus 0.6y?
Oh, so because this matrix must equal that matrix, corresponding entries must be equal. So this equals x, and I get this equation. And I subtracted x from both sides. I just brought the x to the other side.
Okay. Oh, and when you subtract.
So it's 0.5x minus x is minus 0.5x.
Yeah.
And that's problem 1. It's important to know how to do that, even though I probably won't ask you a question where you only have to do that. So a problem like problem 6 is a really nice Markov chain problem. You also have to find this as well as other things. So probably if I had to choose one problem to be on a test, it would be something similar to 6 for Markov chains. And I'd probably ask you some conceptual questions like in problem 8 and 9 with larger Markov chains, where you won't really have to do any computations, you'll just answer some questions about it. Well, problem 6, very important kind of problem to know. How to do. So, new rapid transit system has just started operating. In the first month of operation, 45% of commuters are using the system, while 55% still travel by car. The following transition matrix came from records of previous transit systems. What is the initial state matrix? They call it S0. I mean, we use S1, but it's the same. What is the initial state matrix? Yeah.
It's 0.45.
Right. It's what they told you is going on in the initially. So 45% are using the system, while 55 still use car. So let's use state 1 to be the transit system, and state 2 is they are traveling by car. What percentage of commuters will be using the new system after a month? So we're given that the transition matrix was given 0.7, 0.3, 0.4, 0.6. How would you know how many are using it after a month? Yeah.
You multiply the initial state by the transition matrix.
Right. You find S1, which is going to be S0 times P, which is going to be 0.45 times 0.55, 0.7, 0.3, 0.4, 0.6. And that is going to be 0.45 times 0.7 plus 0.55 times 0.4. And separately 0.45 times 0.3 plus 0.55 times 0.6. What were the numbers here?
0.535.
535.
0.465.
So that so percentage using it after 1 month. So people using transit, 53.5%, and people using car, 46.5% after 1 month. After 2 months, well, that just means you do this again. You find the state at 2 months. That's just going to be the state at 1 month times transition. That is going to be, now you're going to take this guy, 0.535, 0.465, multiplied by 0.7, 0.3, 0.4, 0.6. This is 0.535 times 0.7 plus 0.465 times 0.4, 0.535 times 0.3 plus 0.465 times 0.6. And that one was?
That was 0.5605.
So, after 2 months, uh, 56.05%, we'll use the transit, and 43.95% we'll use car. How many percent, what percentage will use it after it's been in service for a long time? This is C. After a long time. What does that one ask you about?
The steady state.
That's the steady state of the stationary matrix. So, you'd set that guy up again, 0.7, 0.3, 4, 0.6. So this would mean 0.7x plus 0.4y equals x, and 0.3x plus 0.6y equals y. I would take just one of these guys. That would be minus 0.3x plus 0.4y equals 0, and then take x plus y equals 1. Solve that as a system. Row 1 plus row 3 row 2 plus row 1. And that would be 0, that would be 7, that would be 3. So this means that your y is 3 over 7 and your x is 4 over 7. And so this means the matrix is 4 over 7, 3 over 7. They wanted percentage though, I think. As a percentage, what is that? 4 divided by 7? 57.14%. And then this one? So this is the people still using the transit system after a long time. So the best they can hope to achieve in the long run is servicing 57% of the population. And this much we'll use cars after a long time. So whenever something talks about a long time, it's talking about the limiting state, like if you keep doing the multiplications. So if it's asking about a state after a long time, you want the steady state matrix. If it's asking you what does the transition matrix look like after a long time, it's talking about the P bar, which is just going to be the matrix where this becomes every row. That's how you write it out. 8. So they gave you a transition matrix. 0.4, 0.3, 0.1, 0.2, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. This is A, B, C, D. This is called 8. Who are the absorbing states? I know who did it.
C and D.
C and D. Bonus round. Is it an absorbing chain?
Is it yes?
Yes.
How do you know?
Because isn't it just if you, there's a way to get from every like non-absorbing chain to the absorbing chains?
Can we do that here?
So,
So A definitely goes to everybody, including himself. So A goes to B, A goes to D, A goes to C. B goes to C. C goes to itself, it's probability 1, and D goes to itself, probability 1. And so these two guys are the absorbing ones. Is it an absorbing chain?
wasn't it no then because you can't get from B to D?
Exactly, it's a no. What makes it an absorbing chain is that there are absorbing states, but you also have the fact that you can get from any non-absorbing state to any absorbing state. D is an absorbing state, but you can't get to it from B. So, no.
For you to be able to get to it from every.
From any non-absorbing state has to be able to get to any absorbing state. Can't get to D from E. Yeah, so if I ask you a Markov chain problem where you need more than a 2 by 2, there'll be questions like this that I ask you, conceptual ones. Like, could you look at a matrix and know what the absorbing states are and whether it's an absorbing chain? Which means every other variable, anything that you notice is not absorbing, it must have a non-zero probability in the column of an absorbing state. Right? So if B was like 50-50, then it would be an absorbing chain. Right? Because everyone has to have non-zero entries in the absorbing states column. So that's how you can tell from the matrix. But you could also just quickly sketch out a picture and see, can I get to every absorbing state from a non-absorbing state?
Right, so if it's like 0,
9.
0, 3.
So this one actually gave us a picture.
If that was like a 0.5.
A goes to itself,
This is 0, like
0.3. Goes to B with 0.7. B goes to itself with 1. B goes to, or C goes to B, 0.7, C goes to itself, 0.3. Absorbing states. Any absorbing states here?
B.
B. Absorbing chain? Yes. Because these two are not absorbing, but I can get to the absorbing state from either of them. So yes, can get to B from A or C, A and C. And problem 14. We have a manufacturer of clock radios. Comes from 3 different subcontractors. So there's 40% is from 14, 40% come from A, 20% from B, and 40% from C. A though, 1% are defective. And here, 5% are defective. And here, 2% are defective. Okay, so, if a defective clock radio is returned by a customer, what is the probability it came from A? What probability are we looking for? Conditional. It's a conditional. What are the conditions?
I say that given is A,
Given?
probability is A, given that
Right. And what probabilities do we have?
We need probability of A and B occurring over probability of B.
When it says 40% from A, what probability is that telling us? Probability of A. When it says 1% of them are defective, what is probability is that telling us?
probability of B given A.
This is the probability of D given B. This is the probability of D given C. So, in other words, I want to find a conditional probability, and what I know is all the conditionals in the reverse order. What do we use? Bayes' theorem. That's a prime. So, Bayes' theorem. So this is going to be equal to probability of D given A times the probability of A over pretty much all the other guys with this kind of thing. Probability of D given A, probability of A plus probability of D given B times probability of B plus probability of D given C, probability of C. And so this is going to be 1%, 0.01 times 40% over 1% times 40% plus 5% times 20%, 0.2 plus 2% times 40%. What was that?
0.182.
So there's an 18.2% chance that it came from A. The others are similar, not really. But it's Bayes' theorem. That's how you write it up. So make sure you know what you're told. So we're told these probabilities, and make sure you know what the probability looks like that you're searching for. And then you can think of, oh, is there a formula that connects these two? And Bayes' theorem is the guy that connects these. So, last class was a kind of a mess. We didn't even want to be here the day before Thanksgiving. So we kind of left one of the problems on a cliffhanger. I'm not going to redo it or rewrite it, but did you guys figure out the secret application? Do you guys talk to the other class? No. Really? Not at all? Why not?
We don't know anybody.
Look, a big part of college is finding out what resources are available to you and taking advantage of them. Why would you not talk to the other class?
Because we learn the same thing.
Do some recon.
They don't know anyone.
What if they had the test before you? You're not going to ask them, so what did you bump in? Like, you're not going to...
Oh, they do have a right? They have a person.
Well, I told them what the application was. Remember we had that...
Wait, do we get the same
tourists
test as
traveling
them?
around?
Oh.
Because I expect you guys to be talking to them. Where there were people traveling around this city and we tried to find the most popular city.
Why you don't get the same test?
You remember that one?
That's grading.
That Michael had to like rush out for a test.
Oh, so I did not see you, I guess.
You saw the first part of it. Well, the fun application was, I just wanted to show you an example. Not only that it was cool, but something that you all use, because everyone's always like, oh, this is math class. This doesn't matter. You're paying attention to math class. But Google was the secret application. Like, that's how the Google search engine works, right? So, when I was a little Jhevon, there were many search engines. You know, there's Alta Vista, Axe, Jeeves, Web Crawler, lots of stuff. Everyone had their favorite. But Google in the mid-90s, I think, came out, and it was different. Like, you know, it was very routine to be searching on page 23 of a search engine. Oh, let's click on the next page, trying to find something useful. But Google came out, and suddenly there was this search engine that, you know what, the first page is actually pretty useful. I don't feel the need to go to page 2. And the reason is they envisioned the internet as a huge Markov chain. And they pretty much use probabilities to figure out what is the most popular destination when someone types in this search term. Rank that number 1, as opposed to just straight up looking it up like a dictionary and just let everything that has the search term, just dump all the websites on this page, just don't organize, which is how most search engines did it. But Markov chains, really cool application, it's kind of why Google is Google. It's why Google is synonymous with search. And you guys use Markov chains literally every day. Every time you do a Google search, there's a Markov chain in the background. It's imagining the states as websites and the roads that travel from one state to the other. These are just web links, clickable links that allows you to travel from one website to another, right? So if you have a bunch of users randomly moving around the internet, like you can't predict what they're doing, how can you tell that they're going to go from this website to this website to this website? And what are the absorbing states? What is the website that people go to and then they stay there for a long time? Because that's probably because it's useful. So you envision the internet as a Markov chain, and you organize it based on stationary matrices and long-term transition matrices. And yeah, it's why Google is Google. So it's a very important application, and it's used all over the place. But that's pretty much it. We're done. We're not going to learn anything new. You guys want to have class tomorrow? I don't know.
No.
You want to do a review class? Yeah. Tomorrow's a review class. Make sure you do the 2 reviews that I posted online. Some of you already did it, but those of you who haven't, make sure you do it, and you can ask me whatever you want. Yeah. So it's either going to be the S bar, the E.